I'll be speaking about MRI-guided hierarchical sectioning and stitching of brain blocks for precise alignment of digitized histology to corresponding MRI images. An important and difficult to achieve prerequisite to relating MRI and images of processed tissue is the precise alignment of histology images to the corresponding MRI images. However, there are difficulties. On the side of the tissue, large histology sections cut from large brains, such as humans or macaques, are prone to distortions, as we can see with the big brain here, tears, as we can see here from a monkey histology, and foldings. It is difficult to align them to MRI. In terms of MRI, imaging a whole human brain, and I'm talking even ex-vivo, a whole human brain requires a large bore scanner with limited gradient performance and limited spatial resolution. For example, even a 7 Tesla Terra, the most advanced 7 Tesla scanner, still has 80 millitesla per meter gradient system that limits the resolution. The solution that we propose is MRI-guided hierarchical sectioning and stitching of brain blocks for precise alignment of digital histology to corresponding MRI images. In other words, we want to cut the tissue to small tissue blocks and perform ex-vivo MRI in small bore animal scanners like this one here, which can have 7 to 11.7 Tesla magnetic field, but importantly, the gradient system are at least 5 times more powerful, so we can get to high resolutions. In this project, we built on our previous project. When I say we, it's Setu Bupathi who did most of the work and the collaborators from the lab. So we did previously a 3D printed mold for aligning digitized histology to the corresponding MRI images. The idea is that here a macaque brain, I demonstrate everything with macaque brains here. Obviously, everything can be done in humans as well. So this is a ex-vivo MRI at 3 Tesla, T1 weighted and only 0.6 millimeter cubic millimeter. And I call this the 3 Tesla imaging level 1, okay, the coarse resolution. So we segment the ex-vivo brain and we create a mold made of a 3D printing with slits that allow us to insert blades and cut slabs of this brain that by definition are already coarsely aligned to the MRI. Why do I say so? Because the shape of the brain is complex. There is approximately or roughly only one way to put the brain, the specific brain, into the specific mold. And this way aligns already by default the histology of the slabs to the MRI. So we built on this project, and now what we want to do is to get to smaller tissue sections. So we start again at 3 Tesla with 0.6 cubic millimeter. This is T2 weighted MRI ex-vivo. And you can see the scale, that would be 1 centimeter. And we design a sectioning from level 1, from the entire brain, or in this case, only one hemisphere, from level 1 to level 2. We can see here orange lines that are actually planes with which we designed how we are going to cut into 4 blocks. Again, we use the 3D printed model specifically for this hemisphere in order to cut the lateral block, this block here, and the 3 more medial blocks that can be seen here. So now we are left with level 2 blocks. That would be level 1, these are the cuts, but now we have level 2 blocks that we scan at 0.2 millimeter cubic at a small animal scanner. And each of them is scanned separately. You can see that the details are much higher and much better. And roughly, we position them for the purpose of presentation where they cut from the original level 1 hemisphere. So we have a level 2. Now we go to level 3. We take one of the level 2 blocks for demonstration. This is a posterior block, and we cut it to 3 smaller blocks. And to do that, we again do a block, level 2 block specific 3D printing, and we cut the level 2 block into 3 blocks that are smaller. Then we go back to the small animal scanner and image them, this time at 0.1 cubic millimeter. Next is we cut them. In this case, we use paraffin embedded. We can see here one of the blocks. We embedded it in paraffin, and we cut it to thin slices, 5 micron each, in order to get the histology. In this case, it's a missile. We then delineate the gray matter. I'll demonstrate it actually with other data, not with our block, using deep learning. So here's the demonstration. The red contours were made by a human rater. This is manual segmentation. And as the iterative process of deep learning proceeds, you can see that the blue contours merge and segment pretty well the gray matter in this missile-stained histology. So I'll cut it here, and then we use this method of this deep learning in order to segment the gray matter in one of the tissue slices cut from level 3 block. It's difficult to see here, but that would be missile on the left. Here is the gray matter, white matter segmentation. We superimpose the red curves on the histology. And this image is the same histology tissue, same section exactly, only in gray levels. This would be the histology space. Here is the MRI space. SSFP at 0.1 millimeter isotropic. And that would be the segmentation also done with the deep learning. And here is the histology aligned already to the MRI with the red curves that were superimposed on the histology, from the histology. And here the same red curves from the histology are superimposed on the MRI. So that's how we do the alignment in very small blocks. And actually these blocks, I didn't mention that, but they were obtained from the embedding was in a standard cassette of paraffin embedding. And this means that this width is only 2 centimeters. These are really small blocks. And using standard machinery, we can also stain automatically with machines for immunohistochemistry. And now we want to reconstruct everything. For that, we first stitch level 3 blocks to level 2. These are the blocks, the original blocks that were imaged at the small animal scanner. And this is the final result, the stitching. How do we do that? First, I want to demonstrate that there is a need for non-linear registration. You can see here the level 2 blocks and one of the level 3 blocks. And here you get a 1 minus neighborhood correlation that shows around the surfaces of the level 3 blocks that shows that the correlation with the original larger block needs to be corrected. They are not very well registered. So because we use correlation, this means that we need to go to non-linear. I cannot advance my slides. Any advice?
Have you tried arrow keys or clicking?
Arrow keys. That and let's see if I can. Yeah, now I can advance. So I'll go back to sharing. And to this is the demonstration that we need a nonlinear registration. And to do that, we use surface and vertex features for nonlinear registration. So we perform a surface registration. We use the following features. First, the surface shape. Second, we constrain by the intensity levels on the two sides, the two blocks. We use the intensity levels to constrain the surface reconstruction. And then we use normal vectors. In blue are all vectors that are pretty much aligned to the overall plane of the cutting. So we use them for registering the two small blocks of level 3. And that's how it looks. This is the larger block level 2. Here is just the initial registration, which is linear and volume based. There's no surface here. And that's a rigid registration. And here we have a linear surface registration. So there is some improvement. And lastly, that would be the end result. Obviously, the histology is aligned to the small blocks that are then stitched together to create the larger volume. And that's how we get a larger volume, or in principle, in theory, the entire brain with the high resolution histology aligned quite precisely to MRI. Here is a demonstration of the final output. This is a level 2 block, the larger block, the posterior larger block on level 1 hemisphere. And that would be the 3 stitched blocks, the smaller blocks of level 3, level 1 hemisphere. I would like to thank Setu, who did the majority of the work here, Ricardo, who pursued the deep learning for segmentation, my collaborators, and you guys for your attention. Thank you.
Thank you very much, Dr. Shmuel. Just checking to see if there's anything in the chat. I can see that Alan has posted the civet surface reconstruction, and I guess it's also relevant. It's fantastic. There's multiple attempts, programs to create these macaque histology atlases. Could I ask you to kind of comment on the types of use cases that you see for such an atlas?
Well, I think that, you mean for Atlas of the Macaque?
The one that you're creating, yes.
Oh, for high resolution, going to lamina resolution, high lamina resolution, comparison of histology to MRI. And obviously the macaque is a good model to test methods used in humans where we all know that with humans, we cannot control, we get a brain sometimes many hours after the death. The brain is not fresh anymore, and it's difficult to, not always we have MRI of this brain, etc. So this method allows for verified methods that are used in humans.